Hello class, I'm back here to talk about problem 7. Problem 7 does talk about single server waiting line model with Poisson arrivals and exponential service times. On problem 7, I did say that all formulas are found on page 512 of your book. So right here, these are all the formulas, which I actually have put in Excel and have defined in. Okay, so we're going to be removing this. Um, so right here I put what is the average? The problem says Speedy Oil provides a single server automobile oil change and lubrication service. Already tells you a single server. Customers provide an arrival rate of 2.5 cars per hour. The service rate is 5 cars per hour. Assume that arrivals follow a Poisson probability distribution and that service times follow an exponential probability distribution. Again, this section of the book is called single server with a Poisson probability distribution and a exponential service time. So this is how I define these formulas that I have decided. These are the formulas we're going to be using. Right here, your lambda is always going to be your arrival rate or the average arrival rate. So right here, it says the arrival rate is 2.45 cars per hour. Okay, it's important that you notice that. Um, Over here, it tells you the service rate is 5 cars per hour. So your mu is going to be the average for your service rate. So 5 cars per hour. That's why I have this information here. I put all these formulas and let me explain. You're really just gonna need this four, and I added the other ones, and the reason why I did that because you have been assigned a case called the regional airlines. And not only you're going to be looking at these formulas, you're also going to have to be referring to the formulas from page 517 to 519, if I'm not mistaken, to answer the case. Okay, so here we go. Letter A asks, what is the average number of cars in the system? Well, to determine, and if you notice, I put A and A. The reason is the average number of units in the system. That means they are waiting, but they already input their information in the system. They know they are there. So, however, to define the average number of unit systems, which is L, you're going to need to know LQ. Therefore, we're going to calculate LQ first, which is the average number of units in the waiting line. They haven't been put in the system yet. So first, we're going to know what is the average number of units in the waiting line. With this value, because we have a lambda right here, and we have mu, so we can perfectly calculate this. So once you have this numbers, this formulas, these values, you can go ahead and plug here. So on the LQ, you're going to put the value you define here, plus, and you have your lambda, and you have your mu to determine the average number of units in the system. B is asking for the what is the average time that a car waits for the oil and lubrication service to begin. They already been put in the system. Now they are waiting to be serviced, right? So for their specific oil and lubrication service. So right here, the average time a unit spends in the waiting line is gonna be WQ. It's called WQ, which is the LQ, the same value we're gonna calculate first, divided by your lambda that you have it. And then for C, what is the average time a car spends in the system? The average time a unit, could be a car, a customer, spends in the system, that means waiting plus service time, is W. And to calculate W, you need WQ. So we're going to calculate this first, plus 1 divided by our mu, which we have a mu right here. And lastly, D, what is the probability that an arrival has to wait for service? So the average time a unit, the probability that an arriving unit has to wait for service, sorry. So the probability is going to be your lambda divided by your mu. So let's do LQ first, and then we can calculate at least a couple, and then with WQ we can calculate more. So your LQ, all it is your lambda raised to the second power, which is this, divided by your mu times mu minus the lambda. So let's do it. So we have your lambda raised to the second power divided by your mu times your mu minus your lambda. It's 0. So the average number of units in the waiting line is 0 0.5. Okay, so with this in mind, I can put one more digit or not. Okay, that's fine. Let's put 4 digits. Sometimes it makes a huge difference. Okay. So now that we have this, we can answer A, which is what is the average number of units in the system? That means waiting and being served. So we can go ahead and put it over here, or we can even move this over here and follow the same format from up there. So now we have LQ, don't we? Right here, plus, wait, plus our lambda divided by our mu. Lambda divided by the mu, it's 1. So the average number of cars in this case in the system it's 1. Okay. So B, where's the average time a unit spends in the waiting line? Well, the average time, now we're talking about time. So we can define, depending how much we get in hours, we can define how many minutes. That's why I put it like this. So let's go ahead and do is right here says to calculate the average time a unit spends in the waiting line. All you have to do, you have to get your LQ again. That's why we had to calculate that first. And you're going to divide it by the lambda, right? Right here. Well, you have found 0.220 hours. What I did right here, I multiplied this value 0.2 times 60 because in 1 hour is 60 minutes. So 0.2 hours means 12 minutes. So the average time a unit spends in the waiting line is 12 minutes. Or I could do it again. All I have to do is to multiply the value we found times 60 minutes. And now we have in minutes, okay? Same thing over here. The average time C. Where's the average time again a unit spends in the system? In the waiting line here in the system mean waiting plus the service time. They already being acknowledged. So the average time it's gonna be WQ, which you calculate over here, which is now you have that value. So you could just go ahead and do in minutes, but let's go ahead and do the same way. Equals to your WQ, right? Plus 1 divided by your mu, which is 5. So you have a 0.40 hours. So what is a 0.40 hours? In every hour, you have 60 minutes. So you multiply that value by 60. And then you get 24 minutes. So the average time a unit spends in the system once he already has been acknowledged and is waiting for service is 24 minutes, which if you think about it, that's quite a bit and could definitely be looked at by a manager to see other ways to decrease this amount or, by increasing maybe the number instead of a single server or I don't know. That's exactly what we do that. Why we do that, the waiting line models, so you can see where you at and how you can make it better. Actually, what could you make it better to decrease these minutes? 12 minutes, if I'm in a store and I'm waiting 12 minutes to be acknowledged, I'm not sure if I'll be quite happy about that. So lastly, the probability that an arrival unit has to wait for service. So right here it's saying it takes 12 minutes to be acknowledged, 24 minutes to get my service. So let's see the probability that I have to actually wait for uh, an arriving unit has to wait for the service. So which you're gonna get a percentage, and all you have to do, you're gonna divide your lambda by your mu. Divide your lambda right here, since we can't see down there, divide it by your mu. So you have a 50% probability that an arriving unit has to wait for service, which is pretty high too. Okay, again, and then you would be done with problem 7. Again, I put these values right here. If you would ask the probability that no units are in the system, which all you have to do is to do equals 1 minus the value you just defined right here, which is the probability that no units are in the system, could be also 50%. And then the probability of so many units in the system, and then you could go and calculate all that, which we're not going to do because right now I haven't told you exactly how many I want to know, if it's 5 cars, 3 cars, 2 cars, which you could go ahead and do that.